NENOMATICA, where mathematics meets YouTube excellence. The third law of power. Welcome to this lesson on exponents. Today, we're going to learn about dividing powers with the same base. When we divide powers with the same base, we can use a simple rule. For any real number, a, and integers m and n, where m is greater than n, when we divide a to the power of m by a to the power of n, we get a to the power of m minus n. Let's understand why this rule works. When we write a to the power of m, it means a multiplied by itself m times. And a to the power of n means a multiplied by itself n times. When we divide these expressions, we get this fraction. Now we can cancel out the common factors, which gives us a multiplied by itself m minus n times, which is exactly a to the power of m minus n. Let's look at an example to apply this rule. We want to calculate 2 to the power of 5 divided by 2 to the power of 3. Using our rule, we subtract the exponents. 5 minus 3 equals 2. So 2 to the power of 5 divided by 2 to the power of 3 equals 2 to the power of 2, which is 4. Let's verify this by calculating the actual values. 2 to the power of 5 equals 32, and 2 to the power of 3 equals 8. 32 divided by 8 equals 4, which matches our result using the exponent rule. Now, let's look at another example with the variable x. We want to calculate x to the power of 8 divided by x to the power of 3. Using our rule, we subtract the exponents. 8 minus 3 equals 5. So x to the power of 8 divided by x to the power of 3 equals x to the power of 5. Now, let's look at the formal proof of this rule as shown in the image. We start with a to the power of m divided by a to the power of n. This can be written as a fraction, a to the power of m over a to the power of n. When we expand this, we get the numerator as a product of am times and the denominator as a product of an times. This simplifies to a to the power of m minus n, confirming our rule. It's important to note that in the rule we've used, we assumed that m is greater than n. This ensures that the result has a positive exponent. If m is less than n, we would get a negative exponent, which we'll cover in another lesson on negative exponents. To summarize, when we divide powers with the same base, we keep the base the same and subtract the exponent of the denominator from the exponent of the numerator. This rule allows us to simplify expressions involving division of powers efficiently. Let's start with our first example. We need to solve 6 to the power of 15 divided by 6 to the power of 8. According to our quotient of powers rule, when we divide powers with the same base, we keep the base the same and subtract the exponent in the denominator from the exponent in the numerator. So we have 6 to the power of 15 minus 8. 15 minus 8 equals 7. Therefore, 6 to the power of 15 divided by 6 to the power of 8 equals 6 to the power of 7. Now, let's try a slightly more complicated example. We need to calculate 1/4 raised to the power of 7 divided by 0.25 raised to the power of 3. First, we need to make sure our bases are the same before we can apply the quotient rule. We know that 0.25 equals 1/4. So let's rewrite our expression. Now we have 1/4 raised to the power of 7 divided by 1/4 raised to the power of 3. Since the bases are the same, we can apply our quotient rule. We keep the base 1/4 and subtract the exponents. 7 minus 3. 7 minus 3 equals 4. So we have 1/4 raised to the power of 4. Therefore, our final answer is 1/4 raised to the power of 4. Let's solve one more example. We want to calculate 5 raised to the power of 20 divided by 5 raised to the power of 18. Using our quotient of powers rule, we keep the base 5 and subtract the exponents. 20 minus 18. 20 minus 18 equals 2. So we have 5 squared. 5 squared equals 25. Therefore, 5 to the power of 20 divided by 5 to the power of 18 equals 25. Let's summarize what we've learned about dividing powers with the same base. When we divide powers with the same base, we first make sure the bases are the same. Then keep the base and subtract the exponent in the denominator from the exponent in the numerator. And finally, simplify the result if possible. The formula we use is x raised to the power of m divided by x raised to the power of n equals x raised to the power of m minus n. This rule makes dividing exponents much simpler and faster. Practice using this rule, and you'll be able to quickly solve problems involving division of powers with the same base. We have the fraction a to the 7th times b to the 5th divided by a squared times b to the 4th. Our goal is to simplify this expression as much as possible. For our first step, we'll rewrite this expression by separating the variables. We can break this into two fractions, the ratio of powers of a multiplied by the ratio of powers of b. For our second step, we'll apply the exponent division rule, which states that when dividing terms with the same base, we subtract the exponents. So a to the m divided by a to the n equals a to the power of m minus n. For our third step, we'll simplify the expressions by performing the subtraction within the exponents. 7 minus 4 equals 3, and 5 minus 2 equals 3. For our fourth step, we can use the power property to further simplify this expression. The rule states that a to the n times b to the n can be written as the product a times b, all raised to the power of n. So we've simplified our original expression to a times b, all cubed. Let's verify this makes sense. We had a to the 7th over a to the 4th, which gives us a cubed, and b to the 5th over b squared, which gives us b cubed. So our answer is a times b, all raised to the 3rd power. Let's move on to a more complex example. We have the fraction a to the 37 times b to the 40th times a to the 4th times b to the 5th times a cubed times a times b to the 34th, divided by a cubed times b to the 30th times b to the 15th times a to the 5th times a cubed. This looks quite complicated, but we'll break it down step by step. For our first step in this complex problem, let's group like terms. We'll group all terms in the numerator together, all b terms in the numerator together, and do the same for the denominator. For our second step, we'll use the exponent addition rule. This rule states that when multiplying terms with the same base, we add the exponents. A to the m times a to the n equals a to the power of m plus n. For our third step, let's calculate each sum of exponents. In the numerator, the sum of a's exponents is 37 plus 4 plus 3 plus 1, which equals 45. The sum of b's exponents is 40 plus 5 plus 34, which equals 79. In the denominator, the sum of a's exponents is 3 plus 5 plus 3, which equals 11. The sum of b's exponents is 30 plus 15, which equals 45. For our fourth step, we'll separate this fraction into the product of two fractions, one for a and one for b, just like we did in the first example. For our fifth step, we'll apply the exponent division rule again. For the terms, we have 45 minus 11, which equals 34. For the b terms, we have 79 minus 45, which equals 34. For our sixth and final step, we can use the same power property we used earlier to further simplify this expression. Since both a and b have the same exponent of 34, we can write this as a times b, all raised to the power of 34. Let's summarize what we've learned today. We've seen how to simplify complex expressions with exponents by, first, grouping like terms together. Second, using the exponent addition rule when multiplying terms with the same base. Third, using the exponent subtraction rule when dividing terms with the same base. And finally, using the power property to simplify expressions where different bases have the same exponent. These rules are powerful tools that will help you tackle even the most complex exponent expressions. Today, we'll work through two examples that demonstrate important exponent rules. Let's start with our first example. We need to simplify the expression a to the power of 132 divided by a to the power of 72 all over a to the power of 37 divided by a to the power of 17. Let's simplify this step by step. First, we'll apply the division rule for exponents, which states that when we divide powers with the same base, we subtract the exponents. So, a to the power of 132 divided by a to the power of 72 becomes a to the power of 132 minus 72. Next, let's calculate the differences in the exponents. 132 minus 72 equals 60, and 37 minus 17 equals 20. Now, we'll apply the division rule for exponents one more time. When dividing powers with the same base, we subtract the exponents. So, a to the power of 60 divided by a to the power of 20 becomes a to the power of 60 minus 20. Finally, we calculate 60 minus 20, which equals 40. So, our final answer is a to the power of 40. Now, let's move on to our second example. We need to simplify the expression a to the power of 76 plus a to the power of 78 all over a to the power of 4 plus a to the power of 2. Let's simplify this step by step as well. First, let's factor out the greatest common factor from both the numerator and the denominator. In the numerator, we can factor out a to the power of 76, and in the denominator, we can factor out a squared. Notice that in both the numerator and denominator, we have the expression 1 plus a squared, but in different orders. We can simplify this to a to the power of 76 over a squared. Now, we can apply the division rule for exponents. When dividing powers with the same base, we subtract the exponents. So, a to the power of 76 divided by a to the power of 2 becomes a to the power of 76 minus 2. Finally, we calculate 76 minus 2, which equals 74. So, our final answer is a to the power of 74. Great job! Let's summarize the key rules we used in these examples. 1. When dividing powers with the same base, subtract the exponents. A to the power of m divided by a to the power of n equals a to the power of m minus n. 2. When simplifying expressions with multiple terms, factor out common powers to make the simplification easier. 3. Always look for common factors in both numerator and denominator that can be cancelled. Remember these exponent rules, and you'll be able to simplify even the most complex expressions with exponents. We have a fraction with a product of terms in the numerator and a power in the denominator. A times a squared times a cubed times b squared times b cubed, all over open parenthesis, a times b close parenthesis to the fourth power. Step 1. Let's begin by grouping like terms in the numerator. We can rearrange the numerator to group all a terms together and all b terms together. So we get open parenthesis, a times a squared times a cubed close parenthesis times open parenthesis, b squared times b cubed close parenthesis, all over open parenthesis, a times b close parenthesis to the fourth power. Step 2. When we multiply terms with the same base, we add the exponents. So a times a squared times a cubed becomes a to the power of 1 plus 2 plus 3. Similarly, b times b squared times b cubed becomes b to the power of 1 plus 2 plus 3. Our expression is now a to the sixth power times b to the sixth power, all over open parenthesis, a times b close parenthesis to the fourth power. Step 3. Now, let's focus on the denominator. When we raise a product to a power, we distribute that power to each factor. So, open parenthesis, a times b close parenthesis to the fourth power becomes a to the fourth power times b to the fourth power. This gives us a to the sixth power times b to the sixth power, all over a to the fourth power times b to the fourth power. Step 4. Now we can apply the quotient rule for exponents. When dividing terms with the same base, we subtract the exponents. So a to the sixth power divided by a to the fourth power equals a to the power of 6 minus 4. Similarly, b to the sixth power divided by b to the fourth power equals b to the power of 6 minus 4. This gives us a to the second power times b to the second power. Step 5. Finally, we can rewrite this in a more compact form. A to the second power times b to the second power can be written as open parenthesis, a times b close parenthesis to the second power. So our final answer is open parenthesis, a times b close parenthesis to the second power. Now, let's move on to our second example, which involves more complex arithmetic with exponents. Let's examine our second example. We have another fraction, but this time with a sum in the numerator and a difference in the denominator. A to the power of 1,378 plus a squared, all over a to the power of 50 minus a to the power of 48. Step 1. Let's start by factoring the denominator. We can rewrite a to the power of 50 minus a to the power of 48 as a to the power of 48 times open parenthesis, a squared minus 1 close parenthesis. This is because we can factor out the common factor of a to the power of 48, leaving us with a squared minus 1 in the parentheses. Step 2. Now, let's look at the numerator. We can factor out the lowest power of a, which is a squared. So the numerator becomes a squared times open parenthesis, a to the power of 1,376 plus 1 close parenthesis. This is because a to the power of 1378 can be rewritten as a to the power of 2 times a to the power of 1376. Step 3. Now we can simplify our expression by dividing common factors. We divide a squared in the numerator by a squared minus 1 in the denominator, and we have a term a to the 48th power in the denominator, which gives us a to the power of 1376 plus 1 all over a to the power of 46 times open parenthesis a squared minus 1 close parenthesis. Let's examine this example where we need to simplify the expression a to the power of 1378 divided by a squared all over a to the power of 50 divided by a to the power of 48. Let's start by using our first law of exponents. When dividing expressions with the same base, we can subtract the exponents. So in the numerator, a to the power of 1378 divided by a squared becomes a to the power of 1378 minus 2. Computing the subtraction in the exponent, we get a to the power of 1376 in the numerator. Now, let's apply the same law of exponents to the denominator. When we divide a to the power of 50 by a to the power of 48, we subtract the exponents to get a squared. Computing the subtraction in the denominator's exponent, we get a squared. Now, we can use another important law of exponents. When dividing expressions with the same base, we can rewrite it as a single expression with the base raised to the power of the difference of exponents. So a to the power of 1376 divided by a squared becomes a to the power of 1376 minus 2. Finally, computing the subtraction gives us our answer, a to the power of 1374. In summary, we've used 2 key laws of exponents to simplify this expression. First, when dividing expressions with the same base, we subtract the exponents. Second, when dividing fractions with the same base, we can subtract the exponents in the numerator and denominator. These laws of exponents are powerful tools that make simplifying complex expressions much more manageable. Let's begin with our first example. If we have the expression a raised to the power of 83 plus a raised to the power of 87, all divided by a to the 8th plus a to the 4th, multiplied by b to the 78th plus b to the 82nd, all divided by b to the 8th plus b to the 4th. Let's solve this step by step. For our first step, let's factor out common terms in both the numerator of the first fraction and the numerator of the second fraction. In the first numerator, we can factor out a to the power of 83, and in the second numerator, we can factor out b to the 78th power. For our second step, let's notice that in both denominators we can factor out a to the 4th and b to the 4th, respectively. This gives us a to the 4th times a to the 4th plus 1, which is just a to the 4th times the quantity a to the 4th plus 1. Similarly for the b terms. For our third step, let's apply the law of exponents, which states that when dividing powers with the same base, we subtract the exponents. So a to the 83 divided by a to the 4th equals a to the power of 83 minus 4, which is a to the power of 79. Similarly, b to the 78th divided by b to the 4th equals b to the power of 78 minus 4, which is b to the power of 74. Now, let's move on to our second example. We have 0.75 raised to the power of 10 divided by 3/4 raised to the power of 7. Let's first rewrite 0.75 in fraction form. 0.75 is equal to 3/4. So we have 3/4 raised to the power of 10 divided by 3/4 raised to the power of 7. For our second step, when we divide powers with the same base, we subtract the exponents. So 3/4 raised to the power of 10 divided by 3/4 raised to the power of 7 equals 3/4 raised to the power of 10 minus 7, which is 3/4 raised to the power of 3. Let's look at the example we need to solve. To solve this problem, we'll apply several exponent properties. First, let's recall the division rule for exponents. When dividing powers with the same base, we subtract the exponents. This means that a raised to the power m divided by a raised to the power n equals a raised to the power m minus n. Let's begin solving our problem. In step 1, we'll apply the division rule to each part of the expression. For the first fraction, a raised to the power 123 divided by a raised to the power 23 becomes a raised to the power 123 minus 23. Similarly, b raised to the power 154 divided by b raised to the power 104 becomes b raised to the power 154 minus 104. We apply the same principle to the second fraction. In step 2, let's simplify by calculating these exponent differences. 123 minus 23 equals 100. So a raised to the power 123 minus 23 becomes a raised to the power 100. 154 minus 104 equals 50. So b raised to the power 154 minus 104 becomes b raised to the power 50. Similarly, 120 minus 70 equals 50, and 7 minus 4 equals 3. So our expression simplifies to a to the power 100 over b to the power 50, multiplied by b to the power 50 over a to the power 3. Before we continue to the next step, let's review how to multiply fractions. When multiplying fractions, we multiply the numerators together and the denominators together. In step 3, instead of directly multiplying the fractions, let's rearrange the terms based on their bases. We'll group all terms with base a together and all terms with base b together. This means we have a to the power 100 over a to the power 3 multiplied by b to the power 50 over b to the power 50. Now we can use the division rule for exponents again. Remember, when we have the same base in the numerator and denominator, we subtract the exponents. So a to the power 100 divided by a to the power 3 equals a to the power 97. In our final step, we calculate 100 minus 3. Since 100 minus 3 equals 97, our answer is a raised to the power 97. Welcome to this math video. Today, we'll be solving a problem from physics about comparing masses. Let's understand how to solve it step by step. Here is our problem. The mass of one hydrogen atom is approximately 10 to the power of negative 24 grams. How many times greater is the mass of a 100 kilogram weight compared to one hydrogen atom? To solve this problem, we need to first convert the 100 kilogram mass to grams, and then divide it by the mass of one hydrogen atom. Let's start by converting 100 kilograms to grams. We know that 1 kilogram equals 1,000 grams. So 100 kilograms will be 100 times 1,000 grams, which equals 100,000 grams. We can also write this as 10 to the power of 5 grams. Now, to find how many times greater the 100 kilogram mass is compared to the hydrogen atom, we divide the mass of 100 kilograms by the mass of one hydrogen atom. When dividing powers with the same base, we subtract the exponents. So 10 to the power of 5 divided by 10 to the power of negative 24 equals 10 to the power of 5 minus negative 24. That's 10 to the power of 5 plus 24, which equals 10 to the power of 29. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.